Hi, welcome to the fourth video in the EPR series. This is going to be a little bit more on hyperfine splittings, and we're going to try to simulate experimental data. So first, I want to show what happens when you increase the number of nuclei and what happens to the resolution of those hyperfine lines. So we will start with a set of 3 nuclei, copper and 2 nitrogens, and I have included this line here that says numbers. That would be the number of equivalent nuclei. So we have 1 copper and 1 nitrogen of a given hyperfine splitting value and another nitrogen of that hyperfine splitting value. And the hyperfine values that we're going to take are first 80 megahertz and 5 and 5 for the 2 nitrogens, then 80 10 10 and 80 15 15, and we are going to do 3 independent simulations that we're going to plot together. So we are calling the EPR isosim function 3 times. So if I just run this, you can see here that at the beginning I have 4 groups of lines. Those 4 groups of lines come from the 80 megahertz hyperfine splitting of the copper. So copper has a 3/2 nuclear spin, so it has 4 hyperfine lines. And then each of those lines will be split into 5 smaller lines with a pattern 1 2 3 2 1 that comes from the 2 equivalent nitrogens. So in the different simulations, I kept the copper hyperfine splitting at the same value, and I increased the value of the nitrogen hyperfine splittings. So then when the nitrogen hyperfine splittings become 15 and 15, the lines from the different subgroups, the 4th groups of lines, start almost overlapping with each other, so it becomes more complicated. If I increased, for example, one of these hyperfine splittings, and I run it again, then it becomes quite unclear what is going on. So this is hard to know beforehand what it could come from. If we put both together, like 25 and 25, they will be partially overlapped. And when you have this kind of spectra, simulation and a knowledge of the structure of your molecule is very important. It's very hard to guess what are the nuclei in there. And all the simulations have been done with a very small line width in millitesla. Millitesla is the magnetic field unit. And this small line width has been done to show better the different details. But if I increase the line width to 0.2 millitesla and run again, then the lines become much less well resolved. At the beginning, it's very hard to resolve the individual nitrogen splittings in each of the copper hyperfine splittings. You can see them if you zoom enough, because still I have few nuclei. But in reality, there are usually in molecules a lot of nuclei, for example hydrogens, that give some small unresolved couplings. So in here I have added 2 hydrogens, each of them with a number of equivalent nuclei equal to 1, and I will add small hyperfine splittings of 3 megahertz to all these simulations. And let's reduce again the values back to the original. Let's go to this value. And we can see here that we can still resolve. So each of these small lines has been split into 3 lines by these 2 hydrogens. The pattern of intensities would be 1 2 1, although it's very hard to see from the simulation. But if I, for example, increase the number of equivalent hydrogens, it becomes more and more difficult to actually resolve the pattern. You can see lines, but it's very hard to know where they come from. So you have to go first, in order to simulate a spectrum like this, you should first focus on the largest hyperfine splitting, in this case copper, try to fit that value, that would be 80 MHz, as good as possible, and then start focusing on the smaller and smaller hyperfine splitting. So in here it is very hard to know what all these lines come from, because the nitrogen and hydrogen hyperfine splitting values are very similar. If I keep increasing these, let's say, and I put them slightly different, which is very normal in any kind of complicated organic molecule, then it takes a little bit longer. But in the case where the nitrogen and hyperfine splitting values are very close, you can almost not resolve anything. So this is an example with copper. We could do the same example. Instead with copper, we could do it with cobalt. And I will reduce this a little bit just to make the simulation faster. Cobalt will have 8 hyperfine lines, and all of them will be split by many small resonances. So let's go now to all the simulations. Will have the same cobalt and nitrogen hyperfine splittings, but we will change slightly the values of the nitrogen hyperfine splittings. All the values that I'm putting here for hydrogens are more or less normal for various organic molecules. For the metal and the nitrogens, it's basically made up. So here you can see that in some cases they can be better resolved, in some cases they can't. But keep in mind that I'm using a very small line width. If I increase the line width, so here for example, you can more or less resolve a lot of resonances, but if I increase the line width to 0.2 millitesla, basically you cannot see anything in any of the spectra. So the line width in many cases is simply the product of, or the result of, many partially unresolved small hyperfine splittings from many active nuclei like nitrogens, hydrogens, and even from the solvent. So in many cases the line width of the spectra is due to that. In other cases the line width is due to a distribution of G values and A values for the main magnetic atoms in the molecule. For example, when you have metals, you can have a distribution of G values that depends on small distributions of geometries of the molecule, due basically to structural fluctuations. So now we are going to try to simulate a more or less complicated EPR spectrum. So this is an organic radical that contains several nitrogens and hydrogens. So I'm going to first to plot this. The black spectrum is the experiment, and the red is the simulation that basically comes from one of the older numbers. So I'm going to rewrite all this. So I know that in this molecule there are 3 nitrogens and there are several hydrogens. So I'm going to first start with the nitrogens. So here we see that the hyperfine splitting, 80 MHz of one of the nitrogens is too large and the others are maybe okay. The small hyperfine splitting of the other nitrogens more or less matches the separation in the experiment. So let's reduce this. Let's put 5. So we have 3 equivalent nitrogens, each with 5 megahertz. So this is in megahertz always. If we run this, we see that it's not enough. We are not describing all the resonances in the spectrum, but the separation for some of them, this line to line separation is more or less okay, but the line width is still too small for my experiment. So for example, I can start by increasing the line width, maybe to 0.1, and I will increase 2 of the nitrogen hyperfine splitting to 10 megahertz. And we see here that the pattern is still off, the G value is off, so my simulated spectrum is to shift to a lower magnetic field compared to my experimental spectrum, so that means I need to correct this G value, maybe to this value. Now it's more centered, so to 1. Now it's almost perfectly centered. So I'm going to increase these values a little bit. So we can see here that we are missing a lot of resonances. What the nuclei we have seem to be not enough to describe the experimental spectrum. So I happen to know what the values are, and I know that I have several hydrogens. So I'm going to add different groups of hydrogens. So 3 more hydrogens. So let's see what we get here. I made a mistake. So now we can begin to see that the pattern, the simulated pattern, starts to become more similar to the experimental pattern, but still this is not enough. So I am going to increase, so I know what molecule this is. I'm going to show you later which molecule, and I know that there's a methyl group which has 3 equivalent hydrogens. So I'm going to put a 3 here. And let's see what we get. And now the pattern starts to become more similar, but still we are slightly off. So I also know the 3 nitrogens are different and they come from a triazole, and these 2 hydrogens actually are or appear to be, because of calculations, to come from the ortho and para hydrogens in a phenyl molecule. So the ortho, I have 2 of those, and I will increase these values. The para has a value, has only 1 hydrogen. I'm going to show you what happened, and now it starts becoming more and more similar, but still, of course, there are details which are off. So I'm changing the values a little bit because I already know what the final values are going to be, but I'm also trying to go step by step, showing how to make this more similar. And now it looks like basically I almost got it right. If you see here, most of the simulated peaks are almost coming at the same position as the experimental peaks. But still, the line width, why do my peaks look more sharper than the experimental ones? That's mostly because of line width. It could also come from a lack of unresolved features. So my simulated spectrum is a little bit simplified compared to the experimental one, and therefore the peaks look sharper. But if I increase this a little bit, it's going to become better. You see how it's just by increasing the line width, it's becoming more similar. So now I will increase it further. And now it's, I would say, quite similar. I'm a little bit off here. So this means when your spectrum, your simulated spectrum, is a little bit shifted to only one side. So if it fits one part of your spectrum, but it doesn't fit the other, that means that your simulated and experimental spectra are not exactly centered at the same G value. So that means I need to adjust the G value a little bit. If I want to shift my spectrum to the right, I need to decrease the G value because the scale is inverse. So I'm going to basically decrease this value a little bit. I cannot decrease it further than 2 because this is a fully organic radical, and completely organic molecules always have G values slightly larger than 2. If you, in order to have values which are lower than 2, there has to be some transition metal there. So cases of G values lower than 2 are usually found when you have early transition metals like molybdenum, chromium, tungsten, and some other metals like those, maybe even vanadium. You can have values of G which are lower than 2. But usually for fully organic molecules, although this is not a fully organic molecule, but still we expect the G value to be slightly larger than 2, or at least 2. So you can see here that we are very close. We are not done, but we are very close. So we see that our experimental spectrum is slightly narrower than our simulated spectrum. So that means that we have to decrease a little bit some of the hyperfine splittings. And maybe what we can do is decrease some of these ones. One of the nitrogens. So in this way, I am getting almost a perfect fit. I can maybe decrease this further. So this simulation, for now, it's good enough. It's not perfect, but you have to notice that what I've been doing is not fitting the experimental spectrum. I am simulating. So I am manually changing the parameters based on my criteria of a similitude between the simulated and experimental spectra. Simulating is better in order to understand what each parameter is doing to the spectrum. It is very important to know if the values for the hyperfine splittings and the number of nuclei that we include, for example, 3 equivalent nuclei of 3 equivalent hydrogens, come from a methyl group that I know it's there. So it makes sense that I included that. It's not random. You should not put random nuclei and try to get a perfect fit, because then you could be basically inventing a molecule. You could be just making up parameters that don't make sense. EPR is a very precise technique. Sometimes you cannot resolve all the splittings, but when you can resolve many splittings, you can get very accurate information on which nuclei are contributing. So in many cases, now we can do electronic structure calculations that can give us the hyperfine values with a good precision for many nitrogen, hydrogen, and other types of organic or non-metal types of magnetic nuclei, phosphorus, phosphorus, fluorine, etc. So we can use those values to see if our simulation makes sense. In here, I am not getting a perfect simulation because for doing that I would probably either would need to play around more with the parameters, adjust the values more precisely, or do least squares fitting. What I usually do is try to first simulate the spectrum to get as close as I can manually, and then use those values, would be all these A1 values. I will use them as the starting values in a least squares fitting. But doing the approximation first manually, I think it is much more instructive, and also it is much less prone to error than just fitting spectra. You can get a lot of numbers which actually are not correlated with the real values in the molecule. So this was a not so trivial example. I hope it has helped to illustrate a little bit how to simulate some spectra. And that's all for now. I will show you now the molecule. And if you found this useful, please like and subscribe, and also share it with other people. So to show you the molecule, this is a mesoionic carbene complex of gold. It has 3 nitrogens here, a phenyl substituent, and the methyl group bound to one of the nitrogens. This is a spin density plot that shows that the 3 nitrogens have similar, although not equal, spin densities, and also their spin density on the ortho and para hydrogens. The spin density on the methyl groups is not observed at this at the ISO value this was plotted, but there's some spin density here that causes the hyperfine splittings from the hydrogens. So if we see here, the 5.7 MHz values would come from these methyl groups, and the 18, 12, and 9.5 MHz couplings would come from the different nitrogen groups, from the different nitrogen atoms, and then these are the values from the hydrogens that are bound to these carbons. So these results were published by Bergius et al. In Chemistry European Journal this year. Thank you very much.